Okay, nice. Okay, so first, are there questions about the first part that came out maybe during the break? Okay, no questions, I guess. Okay, so let's now deal with the problem of the so-called quantum counting. So, okay, wrong. Quantum counting. So the problem is to determine the value of M, that is the number of solutions. Okay. Now, how do we do this? First of all, it's crucial, once again, to remember that, wrong. Oops, sorry. The oracle is always given to us. Okay, so I mean, somehow in the oracle, it will be written in some way the number of solutions, right? If we have a function which can determine whether something is a solution or not, the function also knows, in some sense, how many solutions there are in the search set. So it means that we have to do something with the oracle, okay? So we can exploit the oracle to know this. Okay. If we have the oracle, this means also that, if you remember, the Grover operator was something like R psi naught. Then, okay, I'll write the identity just to remember that it was the minus space in this case, but it's not extremely relevant. Okay, everything that is here does not depend on the number of solutions, right? They only depend on the psi naught, which is just the uniform superposition of all the possible states, and on the oracle, okay? The oracle, again, encodes the number of solutions in it, but we don't need to access the number of solutions in order to use the oracle. The problem, why do we need to know the number of solutions? Because we want to be able to perform the Grover iterator the appropriate number of times. Now, okay, this Grover operator actually, okay, let's first redefine a Grover operator G tilde just as R psi naught U tilde G. So let's remember that this acts on a minus, but we are ignoring the minus. Again, this is not very important, but just for to be as precise as possible. Okay, now what does the Grover operator do? Actually, what it does is just a rotation by 2 theta naught. So we can rewrite G tilde as a rotation matrix in the bidimensional space. Spanned by S and S naught. Right? Okay, sorry. That's orthogonal. Nice. How do we write this? So G tilde, the form of the rotation matrix is quite standard. So a 2 by 2 rotation matrix is something like this. We know that it rotates by 2 theta naught, so it will be something like this. Minus sine of 2 theta naught, cosine of 2 theta naught. Once again, notice that at this point, we don't know the value of theta naught, right? Because we don't know the value of M. We know the value of L because we still need to be able to prepare the right number of qubits. but we don't know the value of theta naught. If we knew the value of theta naught, we would be directly able to calculate the number of solutions by its definition. Okay, now what we are going to use is a protocol which is called quantum phase estimation. Okay, that's not, I mean, people say that it's not a full quantum algorithm in some sense because it doesn't work by itself. You need to use it together with something else, but I mean, it's not super relevant to us at this point. Okay. So what's the idea of quantum phase estimation? The idea is I have a unitary which depends on some parameter, and I want to be able to determine that parameter. In this case, we are going to apply quantum phase estimation on the parameter theta naught of G tilde. Again, if we get theta naught, then we know that theta naught is the arcsine of the square root of m over L. And since we know m, at that point, we can relatively easily calculate the number of solutions. And once we have the number of solutions, as we said earlier, we can directly calculate the value, the ideal number of iterations. So how does this thing work? Okay, so the idea is this. I'm going to be a little bit quicker on this because I want to move them to the tutorial part. And the problem is that the quantum phase estimation algorithm relies on the quantum Fourier transform algorithm, which by itself takes a lot of time to show the working mechanism. So at some point, we'll just assume that there exists an algorithm which does what we need, and it does. It does actually exist. You can look it up. So okay, let's first identify the eigenvalues of G tilde. The eigenvalues of G tilde have the form lambda plus minus, which is the cosine of 2 theta naught plus or minus I sine of 2 theta naught. If you compute them, and okay, this can be rewritten as this thing here, e to the I 2 theta naught. Okay, please stop me if there is anything wrong at any point. The corresponding eigenvectors of G tilde, so the things which correspond to the eigenvalues are called psi plus minus, which means that G tilde applied to psi plus minus gives plus or minus, gives e to the plus or minus I 2 theta naught psi plus minus. Okay, that's the eigenvalues equation. Okay. At this point, we will use the quantum. We are ready for the quantum phase estimation. So how does the quantum phase estimation work? It works like this. I have 0 and okay, no, give me a second first. Okay, so let's define the problem. So let's start with quantum phase estimation. I will introduce the algorithm without considering Grover for a second, and then we will go back to considering Grover, how Grover works. And okay, quantum phase estimation. Okay, so let's introduce the problem in full generality. Consider a unitary operator U, which, okay, has some decomposition, uj, ej, ej. Okay, and so that's like an eigenvalues decomposition and eigenvalues and eigenvectors decomposition. Now we notice that the UJs have a specific form. Okay, this is something we have actually already found for the rotation matrix. So notice that by definition of unitary matrix, this is true. But if this is true, we can rewrite this like this. So ij, this is ui star, uj, and then we have ei, ei, ej, ej. Okay. Nice. Now, well, okay, this is a delta ij. Okay, so what we get is that this is the sum over I, the delta kills the j, and then here we have the ui modulo square and just the ei, ei. Okay, now notice that if this has to be the identity, we know that the identity can always be represented like this. Okay, that's the resolution of the identity. So it means that for all the i's, ui squared has to be 1, modulo square has to be 1 for all i's. Okay, so basically this means that ui is like a phase of modulus 1. And in particular, we can always say at this point that okay, let's use uj, sorry, written my notes, just not to get lost, 2 pi I phi j. Okay, the choice of using 2 pi is just to parameterize phi j as an object which belongs to 0, 1. Okay, you could equivalently choose to define it like e to the I phi tilde j, and in that case, phi tilde will go from 0 to 2 pi. But, I mean, this is the more common framework. Okay, now let's state the problem. Okay, so remember, our purpose in the end will be to use this to find how many solutions there are given the oracle. So, given U, so the unitary, and its eigenvector, it's one of its eigenvector, find the phase of the corresponding eigenvalue. Okay, it looks like we are going quite far, but we are not actually. Okay. Nice. Okay, so let's first improve a bit the notation. So I will define a u, which is just an ej, so the eigenvector. And I will also define, I will also call phi, the small phi, the equivalent, like the corresponding phase of the corresponding eigenvalue. Now, okay, we can always represent a decimal number, which phi at this point will be, since it's between 0 and 1. We can always binary representation of phi. This will be something like 0 point, and then numbers, phi 1, phi 2, phi 3, where every phi k belongs to the set 0, 1. It's a binary digit. Furthermore, we know that we can write phi as the sum over k of phi k to the minus k. This is just like a decimal representation, but done in binary. Okay. Okay, we need to assume something. So we assume that we can do controlled power versions of U. What does it mean? I mean, U again is like a black box in this case. In the Grover case, it will be just the oracle or the rotation matrix. But yeah, the rotation matrix. So we assume that we are able to do something like this. So a controlled unitary, controlled from like qubit k, and we are able to perform a power of this unitary. Okay, so we basically assume that we are actually able to control the unitary. This is not at all obvious, but it's something that we need to assume in order to be able to perform the estimation. Okay, questions about the statement of the problem of the parameter of the quantum phase estimation? Can you still hear me?
Yes, we hear.
Okay, wonderful, perfect. So just wanted to be sure not to be talking by myself. Okay, so we can perform this object. Now I'm going to draw the phase estimation circuit. Okay, why we use binary representation? Because we want to use qubits in the end. I mean, as you will see, we are going to represent this thing using bits or qubits. So basically, the only way is to use a binary representation. You would need to use objects which can store 10 different levels, but they are not commonly used, neither in classical nor in quantum computation. Yeah. Okay. So given all of this, let's draw the circuit. So this is the quantum phase estimation circuit. I'll first draw it and then try to explain why it works. Okay, so we have n registers. Okay, could you please explain why is the okay, yeah, of course. So we will see directly in the circuit. Anyhow, the idea is that we can perform a power of u. So we can just perform u squared, u to the third power, so u times u times u, or something like this. Second, that's controlled, which means that we can assume that we can perform u according to the state of another qubit. In other terms, you remember that you have the X gate, which is a NOT, basically, and you have the C NOT gate, okay? So, which is a NOT, but it's conditioned by another qubit, which means that if the other qubit is in 0, we will not perform the NOT. If the other qubit is in 1, we will perform the NOT. So yeah, that's the controlled power version of u. Assuming that we can perform a power of u is not difficult. Like if we have u, we can just reapply u. The fact that we can do it in a controlled way is a little bit trickier, but yeah. Is that clear, Sasha? Thanks. Okay. Very nice. So first of all, we do something which is very typical. You do it basically all the time right after the beginning. So we create the uniform superposition of all the possible objects. And once again, this is done by applying the Hadamard gate. Okay, now, so we basically have, as I was saying, n registers for the input plus one register which contains the eigenvector u that we assume to have. Okay, nice. I mean, the eigenvector potentially could be a very large eigenvector. We could have a very high dimensional unitary. For the sake of simplicity, we'll assume it to be like just one qubit, but this is not the constraint. It's like without loss of generality. Now, okay, since we are able to perform a controlled unitary, let me draw this thing here. Okay, nice. Now, okay, we can perform a controlled unitary here. We can perform another controlled unitary here, but then now it's u to the second. We can perform another controlled unitary here, but now it's u to the fourth. Okay. Okay, and so on. Give me just a second. Should not draw so long lines. Okay. Okay. And then we keep doing the same until the last, which is the first. And on the first, we apply 2 to the n minus 1. Sorry, n minus 1 should be here. Yes. Okay. The control version. Now, we notice that since U is an eigenvector of U, like small u, cat U is an eigenvector of big U, it means that we keep applying an operator which has U as an eigenvector to its eigenvector. So at the end, we will always have U, right? We remember that by definition of, okay, U times a phase, honestly. Like we remember that the definition of eigenvector is exactly this. So in this case, we have 2 pi I phi U, right? Okay, at the end here, we will instead have some state, which we will call big psi of phi, which is an n-qubit state, okay? Now, why should all this machinery work, and how should all this machinery work? Okay, I mean, I'm going to show you a single step, like how one of these steps work, and I hope this will give an idea of the general working principle of the thing. Okay, so let's, for example, consider the step which is the ck to the n minus k. So let's assume that I'm taking some one of these. So t, no, should not be here, should be here. So I'm taking 0k here. So if I'm taking 0k, I have to apply u to the power of 2 to the n minus k. And I have to apply it, I mean, in principle, there is all the set of all the qubits which do not intervene in this condition interaction. You see that the interaction always happens between one qubit in input register and the last qubit. So we don't need to take them into account. We will ignore them for now. So we will apply it like this, okay? Again, okay, I'm sorry. Sorry. Okay, so again, there are a lot of other qubits, but nothing is going to happen to them, so we can just forget that they exist, basically. Now, okay, we have then a unitary which depends on the state of xk in order to be applied, right? So every time we have something like this, we can always think to this in this way. So if xk is 0, then the unitary is not applied. So the outcome is xku, right? If instead xk is 1, then the unitary is applied. So the result is xku applied to u. Sorry, u to a power. U to the 2n minus k applied to u. Yes. Now, to write it in a quicker way, we can do this. So cuk to the n minus k, xk tensor u. Okay, we know that u applied to u gives e to the 2 pi I phi u. So if you apply u to the power of 2n minus k applied to u, we will have that this phase comes out 2 to the n minus k times. And so we get something which is the exponential of 2 pi I phi 2 to the n minus k u. Okay, now since nothing happens when u is not considered, when xk is equal to 0, what happens here is that we get something which is this exp 2 pi I phi xk 2 to the n minus k. Here there is a little trick. So this is xk tensor u. Here there is a little trick which comes from the fact that xk equal to 0 means that nothing happens. Exp of 0 is just 1. Okay, so this what happens is basically that you see that the second register is always left unchanged. This effect, which somehow we can also find the minus sign, if you remember in the phase oracle for Grover, is called phase kickback. Okay, so the idea is I apply something which is controlled in some sense, but the effect happens on the control in the end. And it's related to phases. Okay, so where do we get, like, why is this useful in some sense? Because if we put together what happens to all qubits in the entire, so the final state, the state here, this state is 1 over 2 to the n half. And then we have from 0 to 2 to the n minus 1 exponential of 2 pi I, sorry, I should use x, not n here. 2 pi I phi x, and then here you have x to the n. Okay, so this is the overall effect of the quantum phase estimation circuit. Why should this be of interest if I want to estimate phi? Okay, so remember that our task is to estimate phi. Okay. Why should this be of interest? Because we can do something which is the Fourier transform. Actually, what we are going to use is the anti-Fourier transform, but you probably know that the difference between a Fourier transform and the anti-Fourier transform is basically a minus. Okay, so we have, okay, so what we do is that we apply this Fourier transform. So the Fourier transform, 1 second, I've not written it down in my notes, so we'll probably get this possibly wrong. 2 to the n minus 1, sum y, which goes from 0 to 2 to the n minus 1, exponential of 2 pi I phi x, exponential of, I will get this wrong, 2 pi I over 2 to the n x y y n. Okay, this should be right. Let me check it 1 second, because I don't want to do a lot of calculations which are all wrong, if possible. Sorry for this. 1 second. Sorry. And okay, yeah, this should be, this is, okay, I'm missing a minus here, but this should be right. Yep. Okay, and what I do now is that I compute 1 over 2 to the n sum for, okay, y, which goes from 0 to 2 to the n minus 1, sum h, which goes to from 0 to 2 to the n minus 1, and then I merge two exponentials. Exponential of minus 2 pi I x, that's common, and then I have y minus 2 to the n phi over 2 to the n, okay, y n components. Nice. Okay, why should this thing be of interest? Okay, the point is, this thing here gives exactly phi in a representation of phi in n qubits. Why? Because this thing here, okay, because this thing here is exactly a representation of the delta function. So if we use sum over all y's, what we get here is like a delta. It's basically like a delta. Give me a second. What we get here, and using also this, so what we get here is a representation of a delta function phi y. This is probably not obvious at all. You can convince yourself this is true. That's kind of the same thing as an integral representation of a Dirac's delta. But I mean, it basically means that all the other situations, so if y is different from 2 to the n phi, then the sum is 0. Okay. Again, I don't think this is very obvious, but it's actually like it works. If you try with a finite number of like with, I don't know, n equal to 3 or 4, it will work. Okay, so we know how to do this. So at this point, what we have to do is just to apply at the end of this thing, we just apply our Fourier transform, the anti-Fourier transform, which is labeled by a dagger, and then we just measure. Okay, and that's it. So we are actually able to estimate a parameter. How do we do for the quantum counting case? What we do is that we estimate the parameter which is encoded in here. So we use this unitary here to start. Okay, so we use the quantum phase estimation on this specific unitary. Again, this assumes that the person has also given us the eigenvector of the unitary, which is probably not obvious. There are ways around this, but I'm not going to discuss them for reasons of time, honestly. Any questions about this? I guess this is the hardest part, also because I had to go a little bit quicker, but unfortunately, I had no time to go into details about this. Okay, yeah, sorry, one thing that I forgot to say. I mean, we assume that there exists the quantum Fourier transform, and it actually does. Like there is a circuit implementation of a quantum Fourier transform that we can use. And the quantum Fourier transform and the quantum phase estimation are also the building blocks of probably the most famous quantum algorithm, which is Shor's factoring algorithm. And yeah, so they are one of the key ingredients of quantum computation. Questions about this? No questions? Could you please? Yes, of course. Okay, nice. Other questions? Do we use the protocol to decrypt an n-qubit state into binaries? What do you mean? N-qubit state into binary? If you want to open the microphone, it could be easier, Yuri.
I mean to read what binary number is represented by an n-qubit state, which is in the enter channel.
Yeah, so yeah, for example, we start with like a number which is 0, 1, 0, 0, 1, and we map it. This is not a quantum thing, like we just prepare a state which is this. And then at some point we make a measurement on the computational basis, which corresponds to translating again a state to a binary number. I wouldn't call it a decryption though. This is like an encoding more than encoding and decoding, I guess, more than encryption and decryption. Is this okay?
Yes, I think. Thank you.
Thank you. Other questions? Sasha, go ahead.
I wanted
to ask what would be an example of the set of the values and the solutions that we talked at the beginning? Like, for example, can it be a set of some, let's say, answers to a mathematical problem, like a solution to an equation, and we have some numbers that are the solutions and others that are not, or it's something else? Could you please say something?
I mean, it can be anything. The thing we have to keep in mind is that it works for unordered sets. Okay, so think, for example, if you want to find the zeros of a function, okay, you are not working on an unordered set. And in most cases, the best thing you can do is not, I try random values, and at some point you will find a zero. That's a really stupid thing to do, right? Mm-hmm. I usually avoid the fact that the set on which I'm searching is an ordered set. Okay, it's in this case, you, for example, use, I don't know, how's it called, like a progressive bipartition of your set. So you start saying, okay, the zero cannot be here, then it's there. Okay, I zoom in, I zoom in, I zoom in, and go on like this.
Like binary
okay,
search.
It's not. Sorry.
Binary search. I think it's what you're
exactly. Yeah. That's the idea. But binary search is usually used when you have some kind of structure on your set, right? If all you have is like a random, like extracting random objects from the set, and that's all you can do, it's not a structured set, and it's where this gives an advantage. I mean, you are totally free to use the Grover's algorithm for a problem where you should use a binary search, but at that point, you don't get any advantage.
So if I understand correctly, the only condition on this set is that we somehow need to have an oracle, so a way to check if an element of the set is a solution or not. That's the only condition. Okay.
Exactly. That's the only condition. Yeah. It's absolutely the only condition. Again, you are totally free to use this algorithm in a more stupid way than you should, but it's probably not. I mean, at that point, the thing is you are improving on a classical algorithm, which is not the best algorithm for the problem. So it's not very useful, probably. Other questions? Okay. If not, I was thinking to move on to the next part, which is like a key skip tutorial. So we will implement the Grover. Oh, sorry. Did I understand correctly that with the help of this protocol? Yes, exactly. So yeah, the idea of the quantum counting algorithm is to find the number of solutions. That's a bit convoluted how we do this. So first of all, we use the quantum phase estimation to obtain the value of theta naught, which is encoded in here. Okay. At that point, once we had that value, we use this. Okay. So the protocol would be like, the way of doing this would be the following. We have the oracle. Okay. We are given the UG, the oracle. We apply the rotation, the R psi naught to the oracle, and this generates this generates the G operator. At this point, we apply the quantum phase estimation on the G and read out the value of theta naught. Once we have the value of theta naught, then we estimate, we obtain M from theta naught. Is this clear, Danilo? Okay, so let me quickly stop sharing this screen and prepare for the second part. Give me just a second. Okay, so what we are going to use for this is a slightly modified variation of what you can find on a tutorial, which is freely available online. I have also sent Anton the GitHub repo with my variation. I mean, it's not hugely different from what you can find online. There are some more comments, some more things that can be of interest. And the idea is to the idea is to see how this works. So let me share the other screen. Give me a second. I think you should be able to see this. Are you able to see my screen at this point? Yeah, good. Another thing, at this point, I'm not able to keep the chat open because I don't have a big screen here. So if you have a question, try to attract attention somehow, because I will not be able to have the chat open at this point. Okay, so, first of all, a little disclaimer. I'm not an expert on Qiskit. My research doesn't involve direct programming on quantum computers, which means that it happens to me to use it, but I'm not a super expert about it. So don't ask me about, I'm not sure I can answer questions about very specific details of the implementation or of why the functions work like this and so on. Sorry about this, but okay. So, what is Qiskit? So Qiskit is a Python library which has been developed partially by IBM, but it should be open source. It's available on GitHub if you want to contribute to the development of the library. It can be installed by anyone, and it allows to create and run circuits for quantum computers. We can both run circuits on real quantum computers or on simulators. In this case, we will only run on a simulator, and the reason for this is mainly that usually, you can send your jobs to real quantum computers, but at that point you enter a queue. There are obviously many people who are trying to do the same, which means that at some point it can happen that you have to wait for a while. So I decided that it's probably better to run it on a simulator now. But if you go online, it's not too difficult to run it on a quantum computer. Most quantum computer, some of the quantum, you can directly run on IBM's quantum computers, and some of them, like the oldest ones, are usually free, while for the most complicated ones, you usually have to pay or to be affiliated with like a research project of which IBM is a part. Okay, so let's get started. This is just there is a message in the chat. So Qiskit is only simulation of quantum computer using. No, it's not only. Obviously you don't have a quantum computer on your desk, which means that you cannot directly run on the quantum computer. You can though send your job, so you can create your circuit and send it to an actual quantum computer, and it will give you back the results. And you can do it inside Qiskit. Okay, you need a thing which is called an IBM Quantum Experience. I'm not sure it's still called like this account. And at that point, you will be able to send your jobs, and that's completely feasible. Again, the reason why I chose not to do this was because I was not sure about the amount of people trying to do the same about the queue. So let's get started. What we are doing is a very simple example, somehow a very trivial example of a Grover search. We are doing this on a space with 8 bits. Okay, so the strings going from 000 to 111. So numbers like integers numbers from 0 to 7. And it's obviously rather trivial. Okay, it's not at all difficult to search for values in a set of 7 of 8 elements. But at the same time, it allows to run in a reasonable amount of time in a not very powerful computer like mine and so on. And I think it's like didactically interesting. Okay, so let's get started. You import some libraries. I'm using Qiskit again. Which you can easily download via pip, I think, or via Conda. And then I'm using NumPy, Matplotlib, like the usual numerical libraries. Okay. Now, as I said earlier, we do not deal with how to build an oracle. The idea of Grover's algorithm is that you are given an oracle. Somehow, someone is giving you an oracle. By the way, this somehow is a weird thing, because in a sense, the person giving you the oracle needs to know the solution, or at least like a way to easily determine the solutions. So it's kind of a bit weird maybe, but that's the game which we are playing at the moment. In this case, the oracle has been designed to identify two solution states, 101 and 110, which means, I will get this wrong, but it should be 5 and 6, I guess. Okay. So how does this work? First, like the procedure is slightly different from what you do on like in normal programming. So in this case, first you use some commands to create the quantum circuit and then you run it. Okay, it's a bit rigid with respect to this. It's not like a normal Python code where you like the code is executed at runtime. So we create a quantum circuit which has 3 qubits. Okay, we have to declare the number of qubits. When you use a simulator, you are free to use, I think, as many qubits as you like. But at some point, the issue is that the memory requirement to store a state grows exponentially with the number of qubits. So at some point, you will just run out of memory and the program will not work at all. Now, okay, we start drawing we start creating the circuit which represents the oracle. And it has been found that this works if we do like this. So this is a control phase gate, control Z gate. This means that it's controlled by qubit 0 and acts on qubit 2. This is controlled by qubit 1 and acts on qubit 2. And okay, we just create a gate. So the UG is the gate. Okay, that's the oracle gate. Okay, fine. As you can see, we are not including in any way the minus the minus state which goes in. Actually, what we are creating here is what we call the tilde UG tilde. Somehow, the fact that we can use this CZ means that we do not need in any way to have this this added minus state. Now, how does the oracle work? So I've done the same here. I'm not super expert at Qiskit, but it always looks very rigid. Anyhow, okay, here, for example, we can set the initial state. We can see how it acts on some specific states. For example, how does what does the oracle do on the 101 state? Yeah, you see that this added a minus. I mean, it's all zeros. And then it added a minus sign here at the beginning, okay? So the starting state would have had a plus here, but it added a minus. Okay, let's now consider a state which is not a solution. And you see that no minuses were added here. I mean, here there are minuses, but they are on a 0, so just numerical precision problems. Okay? So this is actually working as we want it to. So it has to identify with the minus sign the solutions, and with the plus sign the non-solutions. Questions up to this point? No? Okay. One thing that I would like to remark is that here I'm asking the simulator to give me the state. Okay, this is an actual quantum state. This has like a dimension 8 because we are using 3 qubits, so 2 to the third. But obviously, when I run the circuit on a real quantum computer, I cannot have the quantum state. The quantum state is not an observable object, right? And okay, so this is one of the reasons why using a simulator might be of interest. But again, using a simulator means that you have to store in your classical computer an exponentially large number. Okay, as you can see, these are 16 real numbers or 8 complex numbers. So they scale exponentially with the number of qubits, which is quite bad. Okay, so if I had to already if I had to use already like 5 or 6 or 7 or 10 qubits, it would be already heavy. Probably using 50 qubits is completely beyond reach on a classical computer. Okay. Now, okay, this is the psi-naught operator. This is a function which comes from the Qiskit documentation. I'm going to explain you how it works in a second, but for the moment, let's take it as it is. So that's the R psi-naught, so the reflection around the psi-naught. Okay. Again, it's a little bit intricate, but I'm going to show you why it is how it is. But I need to share the iPad again. So give me a second for this. Okay, this is easier. Instead, this is a function which just applies a Hadamard gate to all the qubits at the beginning. So it prepares the initial state. Okay, for some reason, they decided to build a new function for this. Now, okay, how many Grover iterations do we need? Okay, we have 3 qubits. The search space has size L equal to 8, 2 to the n, and we have m solutions too. How many Grover iterations? So here I'm computing the theta naught angle and the optimal number of iterations according to the equations we were using. The optimal number of Grover iterations turns out to be 1, which is one other reason why this is rather boring, but still, okay, this, yeah. So we have to create our circuit by using one single Grover iteration. Now, how does the circuit behave? So initial Hadamards, Grover, oracle, phase oracle, reflection around the initial, the psi naught state. And then at some point, I just measure, okay, measure on the computational basis. Right? Any questions up to this point? No? No questions? Okay. Okay, at this point, we want to simulate what happens, okay? We use this simulator. There are many different simulators available. Some of them can take into account some amount of noise, which is interesting. As usual, quantum mechanics is a statistical theory. So we have to repeat we have to run our circuit many times. In this case, I think it will run, how many? Yeah, it will run 1,000 times, I guess, vaguely, little bit more. Okay, fair. Okay, okay. So we just run our circuit a lot of times, and as you can see, we find basically all the time. Sorry, let me try to remember if I can set the runs to, I don't know, 100. No. Very nice. I don't remember the, okay, there, sorry, I don't remember the argument to set the runs. Okay, so most of the times I get something which is actually my solution, okay? Like actually here all the times. If I had a true quantum computer, I should take into account some decoherence or noise effect. At that point, the performances would be much worse than this. But I mean, this is a rather stupid example in a sense, okay? It's just proving that what we are doing kind of works, that the Grover algorithm is actually able to perform a search. But you can imagine that if we were able to do this on a much larger space, at that point, we could actually achieve a meaningful advantage. Why do we set the theta naught? We don't, give me a second. Where I'm not setting the theta naught, I'm calculating the theta naught. The point is we are given at the beginning the M and the L. So M is 2, L is 8. So someone has given us the oracle and has told us you have 2 solutions and in a space of 8, in a search space of dimension 8. Okay. So that's what they've given us. And at this point, I'm just calculating theta naught. I'm saying that we don't have control on theta naught in the sense that that's completely determined by input data, okay? So I'm calculating theta naught, I'm not setting it. I have no degree of freedom in choosing theta naught. Is that clear? Okay, any other question? Can you tell us a little more about the oracle? Yes, so I cannot tell you exactly how the oracle works because honestly, I mean, building an oracle is not an easy thing to do. There are articles and papers which try to explain how to do it, but it's really beyond the purpose of Grover as an algorithm, and I'm definitely not an expert about Oracle engineering. Now, how does the test Oracle function work? So it's not, I mean, it's actually not a function. I'm just creating a quantum circuit and I'm setting an initial state. So in Qiskit, you always assume that your state at the beginning is completely zero, so 0 in all qubits. So in order to create a 101 state, there is a function to initialize it, but it's just easier to use two NOT gates here and here. And here I'm just copying the Oracle code. So someone has given me this code, okay? I honestly can have some kind of intuition maybe of why it works. But honestly, like the idea of Grover is exactly someone has given me this code. At this point, what I'm doing is preparing a backend. A backend in Qiskit's language is an object which can run a quantum circuit. It can be either a quantum, like a true quantum device, or just a simulator on my machine. And the system is built in such a way that you can seamlessly turn from one to the other. The results at this point have this. Okay, at this point here, you see that I'm running the circuit. So I'm asking it to simulate the circuit and to get the results. And when I ask to get the state vector, it means exactly I want the quantum state. Again, getting the quantum state is something that you can only do on a simulator. Like a quantum computer has no idea of what's the quantum state. It's just doing physics, not like actually, just doing physics. Is this okay? Sorry for not having more details about how to design an Oracle, but honestly, it's really really a tricky thing that I'm not an expert about. Okay. Other questions? When you get yes, of course, I share the link. I mean, okay, if you want, like if you go to Qiskit tutorial Grover, if you Google Qiskit tutorial Grover, you can find the original Grover tutorial, which is very similar to this. I added some comments, this part to test the simulator and so on. Else, it's on my GitHub, and I share with Anton the link of the repositories, and it's public, so you are free to access it. I guess he will share it with you at some point. Yeah. Anyhow, yeah, it's like a slide modification of it. Now, if it's okay for you, I wanted to, yeah, okay, thank you, Anton. And okay, I wanted to quickly show you why this weird diffuser function works. So the Oracle only, yes, and user, exactly, yeah. I mean, it's not an exhaustive search in the sense that it's going to check all the possible values. It's actually a random search. So it's the equivalent of randomly extracting objects. The only thing is we want to make the random extraction more efficient. And yes, the Oracle only determines whether a given object is a solution or not. Yeah. This is true.
Short interruption by me. We will have like a break in 2 minutes, but I think like we can also take some additional 5 or 10 minutes to finish the material if it's required.
If it's okay for you, yeah, it would be great.
It's totally fine. We have a big break, 30 minutes break. So this works like a security people. So yeah. Yeah.
So it's a quick, okay, just a quick thing, like the last thing for today. So let me stop sharing this and try to share the iPad screen. Give me just a second. Okay. Okay, give me just a minute. Oh, sorry. Okay. Okay. Sorry. 1 second. I'll open all right. Nice. And I want to share the one on the right. Okay. Very nice. Okay. Sorry, I had to. I have to take Take my notes, and this is the wrong one. Sorry, I should have prepared this better. No. One second. Okay. This one has to be on. Okay, and now, how do I switch this thing? Sorry. Okay. Doing the right thing, possibly. Okay, yeah. Okay, I should have everything I need. Sorry for the delay, but I did not print these notes and I was wrong. Okay, so how to build, okay, the question is how to build rpsi-not in Qiskit. Because when I found that generate diffuser function, I found it a bit weird. So I wanted to understand the internal machinery. So the idea is what we want to do is something like this. rpsi-not is twice psi-not minus identity. Okay. So in other terms, what we have to do is to add a negative phase to all states orthogonal to psi-not. This is our task. Okay, now, yeah, so the first thing which we notice is that how do we get the psi-not? It's just this, okay? I'm ignoring the fact that it's like a multi-qubit thing, but it's not worse in any way. And we also notice that if we apply Hadamard twice on the state 0, which in other terms means applying Hadamard to the state psi-not, we get again the 0. That's one of the properties of the Hadamard gate. So its square is the identity. Okay, so this means that if we want to rotate around psi-not, we can convert this rotation into a rotation around 0, which is probably easier to do. So how do we do this? We just apply Hadamard to the R0 and then another Hadamard. What's an R0? An R0 is the same thing, but with the 0 vector instead of the psi-not. So that's this. And okay, what do we do now? Okay, okay, how do we implement? So now we map the problem in the problem of how to implement R0. So how to implement a circuit that adds a minus to all components orthogonal to 0. Okay, how to implement this? Now, the idea on which Qiskit does this is this. So we use a multi-controlled Z-gate. How does this thing work? I mean, a multi-controlled Z-gate, in practice, what it does is that, I mean, for our purposes, what it does is that it maps this state into this state. Okay. Now, I want to only change the phase of this thing here, or better, I want to change the phase of everything else, but I mean, I first try to change this phase and then I will see how to get to the phase of everything else. So now I'm able to change the phase of 1, 1, 1, 1, 1. I want to change the phase of 0, 0, 0, 0. So I can just use an X. So if I do something like this, now it's probably better if I explicitly write the fact that it's a multi-qubit thing. Okay, so the rotation, like the rotation, the reflection around psi naught is at this point, this object here. Now the minus is not an issue, because I mean, it's just a global phase. Sorry, this is over around R0. At this point, this is the last thing for today. This is true. So this is how Qiskit does the diffuser. Okay, this is not extremely relevant, like it just to explain that weird function there, which gave me some headache previously. So yeah, I mean, if it's not completely clear, you can probably redo the calculations, for example, and I mean, it's just a matter of algebra. There is nothing very deep in it. Okay. Okay, if this is okay for you, do you want, like, if there are any questions, I'm happy to try to answer at my best. No questions? Okay.
Yeah. As there is no question, I think we can go to the break. Thank you very much, Marco. It was a great lecture. Yeah, thanks.
Thank you. See you.
See you.